Hello, and welcome to a session on technical modeling. My name is Kurt Smithkill, and I'm a CFD and hydraulic engineer with Alden Labs. And today I wanted to present on alternative 2D model formulation to aid hydraulic structure design and no-rise analysis. So when you're modeling for a no-rise, often it's easier to perform a 1D analysis because that's what's more commonly accepted. Most often your legacy effective models are 1D, and that a uniform accepted 2D approach still hasn't quite been established yet. So this often leads to a situation where a more robust 2D model is used for design, and then you have a separate 1D model that's used for no-rise analysis. And I just wanted to give this presentation to share some ideas for how to incorporate a little more robust 2D data into a no-rise analysis that could either be 1D or 2D. So first off, I just wanted to briefly go over a little bit of 2D model formulation and some of the background theory because it's relevant. When most people say 2D model, you most often think of just your generic HEC-RAS 2D, where it's a depth average model, and as the name assumes, there's only a single cell in the vertical direction. And this is great for river and floodplain flows where you have kind of general shallow depths, and it's more important to capture the variation in velocity across a channel than it is vertically within the water column. However, there's also a second type, which I'm referring to as a vertical slice. And in this case, you're looking at the centerline profile of a structure, for example, in the example below, and there's only a single cell in width, so normal to the figure. And this allows you to include cells in the vertical direction so that you can resolve that variation in velocity between the bed and the surface. So since it's important to talk about how the model, how a 2D model is formulated. So this is where for depth average models, to reduce your 3D St. Venant equations to your 2D shallow water equations, you assume a logarithmic velocity profile. And that's the standard law of the wall where as you travel away from the bed, the vertical velocity profile follows this logarithmic pattern. And for most cases with general river flow and turbulent flows, this is good. However, there are two specific areas where this logarithmic velocity profile assumption falls short. And first off, that is flow approaching a hydraulic structure. And then second is flow immediate below a hydraulic structure. So where you would expect to have a hydraulic jump. And here's just a quick animation showing vertical velocity, and then we'll dive into it a little more. So here's just an example of a spillway where you have flow going from left to the right, and it accelerates as it goes down, and you can see you have this resulting hydraulic jump. And it's very turbulent and chaotic, and there's a lot going on there. So back to those two areas where a logarithmic velocity profile doesn't hold true. And first is this accelerating flow near the spillway crest. So as you look in that first yellow circle, you can see the red's higher velocity, and that is where your highest velocity is, and you actually have your slowest velocity is at the surface. So that clearly doesn't follow this logarithmic velocity profile. And then on the downstream end, you have this recirculation region or roller, which is also not following a logarithmic velocity profile, where you have flow going left, right on the bottom, this high velocity jet. And then on top, you have this recirculation region and flow. So you have flow kind of going in both directions there. So that's not able to be resolved with a depth average model. So why does this matter? Well, within a no-rise context, this upstream one's very important. So by accurately resolving this upstream velocity profile, you're accurately determining the rating data for this structure, because you have this nape as it accelerates down. And within the context of a no-rise, this is your rating data. If you get this off, you could be underestimating a rise or overestimating it. So this is where the vertical velocity profile is very important when modeling hydraulic structures, especially if you're trying to meet a no-rise condition and want to have the least uncertainty possible. To a second extent, you also are able to resolve the hydraulic jump. And similar to your presentation last year on the hazards of low head dams, this is that roller or recirculation region where there can be a public hazard or safety hazard where people could get caught in this recirculation region. By modeling this vertical velocity profile, you're able to resolve the flow structure of that hydraulic jump. And by doing so, you can determine if you'll have this recirculation region. You could even go so far as to find modifications to remove it or tweak it. And this has safety and recreation impacts. And a third reason too is that with this vertical velocity variation, you can see there's higher velocity on the bed at the outlet in the region of this hydraulic jump. If you're using a depth average model, you're numerically diffusing that out. Whereas in here, you can see it's a high velocity, so that by doing this, you'll get more accurate shear stress calculations based on this higher velocity jet that's striking the bed. So to walk through how these different models can be used, I just wanted to go through this example project just to demonstrate the workflow. So to start off, I just wanted to describe the background and then show the effective model prior to showing any site photos, just to see how reality is compared to what you imagine. So for this example, a dam in the Northeast needs to install a new fish ladder to provide upstream passage for Atlantic salmon. So that's a good thing, all right? We're retrofitting an existing hydroelectric station to facilitate upstream passage. However, by adding this proposed fish ladder on the existing spillway, it's blocking it, rendering it ineffective. So you're losing capacity by putting this structure in. So to compensate for the loss of length in spillway, the existing dam crest is to be notched where adjustable Obermeyer gates are going to be added. So here's the 1D effective model. And there's a couple pertinent features here you can see. On the kind of on the left, you can see this is what was called a railroad abutment in the model. You have two abutments that correspond to pedestrian bridge without a deck. And then also kind of significant is you have this approach flow where you see there's a general channel width, but then at the cross section where the dam crest is, it gets much wider. And then downstream below, it gets much narrower as it flows under a road bridge. So here's the real life conditions. And this is where it's quite surprising, where upstream, you can see the pedestrian bridge. However, the abutments don't appear to be actively in the channel. For this railroad bridge, you have several abutments, not just one. But then probably the most interesting one in terms of hydraulic modeling is the fact that this spillway is an L shape, where part of it is perpendicular to the flow, and then some of it's kind of this oblique angle, which makes it interesting. And then you also have this irregular bedrock below the channel, which makes it very chaotic and turbulent and hard to model accurately. So here's this kind of a larger schematic summary, the same thing. You have this pedestrian bridge upstream. You have the railroad bridge at this oblique angle. Then you have this L-shaped spillway crest with the downstream road bridge, and then the powerhouses on this bottom left corner. So that's quite a bit different from the way it was represented in the effective model. So in this case, the effective model even had an incorrect total spillway length. And just by nature of a 1D formulation, the spillway was completely in line. All flow is perpendicular to that structure. Where in reality, with this L shape, it's both an inline and a lateral structure, where that northern crest perpendicular to flow, that acts as inline, and the water keeps going down. But then you have that other section of spillway where it flows in from the side, so that acts as a lateral structure. So that'd be kind of difficult to do in 1D. And then also the reach lengths were incorrect, making it artificially steeper in reality. So there's several issues impacting the accuracy of this effective model. So the reason with looking at starting with an effective model was to see how accurate the existing conditions were resolved. And based on some of these inaccuracies, it was decided to build new models since there was a lack of information about the hydraulic performance of the existing dam crest. We didn't have any original modeling reports or know any of the real design constraints based on the spillway. And since the spillway is so long, getting it right is very important, because within that context of no rise and floodplain profiles, like any variation in your coefficient of discharge is going to have huge implications on that upstream water surface, which can propagate miles upstream. So it's quite important to get it right. So then how do you resolve this existing dam crest? I mean, you could just pick a coefficient of discharge. So you look up your OG crest, assume it's at your full hydraulic head, and you could come up with a value, say 3.9. Well, there's quite a lot of uncertainty with that. By just picking a static discharge coefficient, you're not capturing kind of two important considerations. The first is just how your discharge coefficient varies with head for a given structure. So the figure on the right shows different Army Corps tests for an OG crest spillway. And you can see that the discharge coefficient can vary anywhere from just over 3 to over 4, which again, thinking about this project and within a no rise, like you really want to have confidence in how you're resolving that spillway. And then a second is reduced conveyance due to submergence. The discharge coefficient curve on the right assumes your tailwater doesn't impact it. But with low head dams, especially once you start getting up into higher flows and say at the regulatory 100-year flow, some of these structures may be backwatered and submerged, and that'll greatly reduce the conveyance of the structure. So to address these uncertainties, both these two different formulations of 2D models were used. First, the HEC-RAS 2D model was used just to get rough approximations for water surfaces to start with. And then second, this vertical slice model is used to compute a unique discharge coefficient for those specific headwater, tailwater surfaces. And then based on that result, you can back calculate out this updated discharge coefficient, which you can then put back into the HEC-RAS 2D model and iterate through the cycle a couple times until you converge to a common value. So this really allows you to accurately resolve the site-specific discharge coefficient of a structure. And then you can take that information, plug it into your 2D HEC-RAS, so you can get the conveyance right in the distribution. So you can really get the best of both worlds without having to go fully 3D, which takes a lot more time and money. So here's how the 2D HEC-RAS model is set up, where you have an upstream flow area here, and then you have a second downstream flow area, 2D flow area here. And then for each unique section of spillway crest, a specific or distinct 2D connection is added. So this way you can impose different discharge coefficients for different sections. So you have a different gate somewhere else. This is just a way to parameterize that crest. And then here's the 2D vertical slice formulation. This is actually done within Flow3D, despite it only being a 2D model. So in this case, this is where you have the 2D slice where you assume symmetry on both sides. So you have this infinitely long spillway, which based on these site conditions isn't too much of an abstraction. And then the geometry was created from the as-built cross-section profile, because without any modeling documentation, we don't really know the performance of this specific shape in this specific setting. So this is where we can use these modeling tools to effectively parameterize it. And after running several combinations of different upstream water surfaces for different flow rates, we could generate this curve. And this is just to show the effect of how your coefficient of discharge increases with hydraulic head. But then after you go really high, you get the submergence, so you get reduced conveyance once you go even higher. So this red dot is the 100-year storm. So that's where it was really good to capture this with both the 2D HEC-RAS and the vertical slice, because your 2D HEC-RAS is kind of getting those submergence numbers. And then by using those water surface elevations in the 2D vertical slice model, you can then get an accurate coefficient of discharge, which then goes back into the HEC-RAS so that you get this system that works really well to describe it. So that was for the existing conditions. And it was actually quite useful for proposed conditions where we had to create this adjustable grate structure to compensate for the loss in spillway. Now, initially, this shape was created with just this trapezoidal section. And by running the vertical slice simulation, you could get a discharge coefficient of 3.05. But as you look, you can see there you have this flow separation region here just on the top of the structure, and then you have this huge one behind it. So those recirculation regions kind of cause drag and reduce the efficiency of the structure. So by curving it and mimicking it and seeing exactly where the gates will lie down, we were able to come up with this streamlined section, and that was able to increase the coefficient of discharge to 3.4, which really had a big impact on the total length of these adjustable gate structures that were needed. So that was a big cost savings to the client. So here's what the kind of the final proposed conditions laid out. Despite having all this other spillway crest on the western side, it was decided or preferred to do this V-gate scenario so that you could increase your total spillway length despite your fixed existing crest length. So by doing this, that was able to, this V-gate configuration with that streamlined profile was able to compensate for the loss of spillway due to this fish ladder, which is just completely ineffective flow in the model. So there's no overtopping at all. Now, here's kind of the hard bit. How do you integrate this within a no-rise? Well, Flow3D isn't a FEMA approved model, so you couldn't just use that to start and try and use it. However, this is where the Flow3D model was used to derive inputs for a FEMA approved model, in this case, HEC-RAS 2D. So that by doing a good technically defensible analysis, you could use these inputs within a FEMA approved model and try and get it approved. So now comes the way of how do you deal with your 2D data. Well, and this, for disclaimer, this isn't well established, and it's really just a matter of trying to come up with something that's both technically defensible and then works well with your local floodplain administrator. I'm a fan of trying to just interpolate your water surface across every 2D cell that touches your cross section. So in this case, you're just reducing your 2D data to a 1D number to match the standard kind of 1D no-res analysis. So if that doesn't work, then you're kind of forced to move to that scenario where you have two separate models. And for something like this, this is where, now that the existing dam crest coefficient of discharge was determined, you could go back in, impart that on that cross section, and do your no-rise comparison that way. And you just might need to average things out across to get the complexity resolved. A key to this is just perform good documentation and develop a good working relationship with your local floodplain administrator. So in conclusion, you can use this 2D vertical slice model to get the benefits of simulating the vertical velocity profile, which allows you to accurately resolve flow hydraulic structures without a full 3D simulation. And like, as these modeling methods and techniques continue to evolve, it's important to keep trying to use the best analysis possible. The floodplain modeling practices are quite established and debatably institutionalized. So it's good to always keep trying to do the best analysis possible. And for this last slide, here's just my contact information. If anyone wants to reach out for any reason, I plan to be on for the Q&A session shortly after this. So thank you.